Okay, TLC. What is the use of TLC? Okay, thin layer chromatography. It helps us to determine how many components are there in the mixture. Okay, another way is to identify purity. Okay, how pure each of the component are there in the mixture. Okay, secondly, it enables us to determine the best solvent condition for separation if we use column. And the thirdly is to monitor composition of fraction collected, okay, from column chromatography. Okay, so what are the advantage of using thin layer chromatography? Okay, it is very sensitive, okay, fast, a simple technique, inexpensive, okay, because we only use a piece of paper or piece of coated silica on aluminium or glass, okay, rather than use the high-end instrumentation that I mentioned early on in the early lecture. Okay, it is a micro technique, means as little as 10 power negative 9 gram material can even be detected. Okay, and the sample size is from 1 to 100 times 10 power negative 6 grams, so we can save a lot. Okay, we only use very little amount. Okay, this is how if we do a thin layer chromatography experiment. I'm sorry you didn't get chance to do this. This is how you spot the sample on the TSC plate. Okay, not too much because otherwise it, it leads to tailing effect. Okay, once we do the spotting, we dip it in a beaker that already filled up with solvent. Make sure the starting line is way above the line of the solvent. Okay, and then let the capillary reaction do the work. Okay, and it will separate the component in the spot. So this is a TLC of black ink. Okay, so black ink is spot here, and then solvent or the mobile phase will separate the component in the black ink. Okay, so it's actually composed of many color. So how do we visualize spot? Okay, it's easy to visualize with our eyes if the component are colored. What if the component is not colored? Okay, means colorless. Okay, so we can use these three techniques here to visualize the spots. The first type is sulfuric acid and also heat. Okay, this visualization technique is destructive because we apply heat. Okay, when we apply heat, we burn the TLC, and what left behind is charred blocks, and that is the spot of the separated component. Okay, the second technique to visualize is iodine. This is semi-destructive because iodine vapor will absorb on the spot. Okay, temporary. Okay, once the iodine vapor vaporize, then the spot become invisible again. Okay, so it's not permanent. So once you see the spot, you can mark it using pencil. The third technique is using UV light, like you normally see in any supermarket to check whether your money is pure money or not. Okay, so they use UV light. So this technique is non-destructive because it only uses UV. Okay, so if we use the long wavelength light, means the background will be green in color and your spot will be dark. Okay, if you use the short wavelength, the plate will be dark but your component, spots will glow. Okay, it's like glowing in the dark. So retention factor RF is calculated based on the distance traveled by the spot or the component over the distance traveled by the solvent. Okay, so remember I mentioned that you have to draw two lines, the original line and the solvent front. Okay, the distance between the original line and the solvent front will be the distance traveled by the solvent. Okay, and the distance from the original line to the center of the spot is the distance traveled by the spot. Okay, and then we calculate RF from there. Okay, this divide with this. So we have 1, 2, 3, 4 spots here. Okay, how to calculate RF? Measure the distance traveled by the spot, divide with distance traveled by the solvent. So this is the original line until to the center of the spot here. Okay, that is the distance traveled by the spot. So the retention factor RF will depends on this parameter here. First one is solvent system. Secondly is the adsorbent. Okay, the stationary phase itself. Okay. Thirdly is the amount of material spot. Okay. So ideally, retention factor value should be in between 0.2 to 0.8. So if you don't get value in between this range, means we have to change any of these three parameter. Okay, normally solvent. Okay, normally solvent. Okay, amount we easily can see because if too much then we can see tailing effect. Okay, macam bereko-eko. So how do we adjust RF, especially solvent system? We play around with the solvent polarity. Normally we use the non-polar solvent first, then if we don't get nice retention factor value, then we change the solvent system to a more polar solvent. Okay, so let's say here we have an example of a thin layer chromatography TLC, and it's a mixture of a two component, which is component A and B. Okay, so this is the original line and this is the solvent front. Okay, depends if you stop here or you stop here, the distance or the RF value between the two value will be the same. Okay, so based on this, we know that component B is less polar because it moves more quickly by the mobile phase compared to component A. Means component A is more polar, more retained by the stationary phase itself. So can you calculate the RF retention factor value for spot 1, spot 2 and spot 3? Okay, to calculate this, you need to measure the distance traveled by the spot from this point to here, divide with the distance traveled by the solvent from this line here to this line here. Okay, so distance traveled by the spot, okay, here to here is about 1.34 centimeter. Okay, you measure from this, not here. Okay, so divide with the solvent front distance. Okay, so make sure you measure to the center of the spot. Okay, so this is how it should be done. Okay, distance traveled by the spot over distance traveled by the solvent front. Distance traveled by the solvent, sorry. So this would be the retention factor value for each spot. Question: which of these sample 1, sample 2, and sample 3 compose more than one substance? So if your answer is 1 and 3, that is correct. But if you answer 2, also correct, okay, means the solvent used for sample 2 probably not suitable solvent system. Remember the 3 parameter just now, especially solvent system. So probably for sample 2, solvent is not suitable, so you have to change the solvent because it's not separated. You see, it moved almost to the solvent front already. Okay. So next we move to column chromatography. So column chromatography, different with TLC or paper chromatography, because for the stationary phase we use a fine solid pack, okay, pack in a column. Okay, so that will act as the stationary phase. Okay, mobile phase still is the solvent used. Okay, it will be poured at the top of the column and it will flow down through gravity action. Okay, normally column chromatography is used as a purification technique. Purification technique means we want to purify the component in the mixture. Okay, so this is how a packed column looks like. It looks more like a burette, but it's slightly bigger in diameter. And then we pack very fine silica gel as a stationary phase here, and we put a small amount of glass wool here so that the silica gel would go through the hole here. Okay, so we stop it here. Okay, so when we pour inside the mobile phase along with the sample component, it will travel down and out here. Okay, again concept: polar likes polar, non-polar likes non-polar. Polar component will be retained by the polar stationary phase, okay, and the non-polar component will move faster down the column. Okay, so this is how example. Okay, so we load our sample here. This sample is composed of 3 component: component A, B, and C, component red, green, and blue. So here we see A is non-polar because it moves faster. Okay, so it will be collected first, followed by component green, which is considered as semi-polar, and then lastly component blue, which is the most polar component. Okay, because it moves slower. Okay, so it was retained by stationary phase. Okay, so this is how it works. I have explained this. Okay, just read through. Okay, and then you collect the sample at the bottom of the column. So the stationary phase for column chromatography is either silica gel or alumina. Okay, and they are sold in different mesh size. Okay, for example, silica gel 60 or silica gel 230 to 400. Okay, the number will refer to the mesh, okay, of the sieve used to size the silica. So means 60 will be smaller compared to 230 to 400. Okay, so this will be more packed because the size will be smaller. Okay, so means the separation will take longer. Okay, okay, solvent, which is the mobile phase, okay, will be used to carry the sample, okay, down the column or upwards to TLC or paper chromatography. Okay, um, Normally we use non-polar solvent first. Okay, this non-polar will elute the non-polar component first, and then once we have elute the non-polar component, then we change to a more polar solvent to elute the more polar component. Okay, so means we want um, to move the polar component which have strong affinity to the stationary phase. Remember, the stationary phase is polar. Let's say the sample is polar, so it will be retained. So how to move that retained polar component? We use a polar solvent. Provided a polar solvent has have more stronger attraction to the sample compared to the attraction between the sample and the stationary phase. Okay, so the attraction is normally by hydrogen bonding or dipole-dipole attraction. So these are the different polarity of different solvent. Carboxylic acid is the most polar solvent. The least polar is the alkane group. Okay, the one in between is aldehyde, ketone, and also aromatic hydrocarbon. Okay, specifically, these are the example of alkane. Example of alkane is hexane, petroleum ether. Example of carboxylic acid is acetic acid. Okay, so these are the example of solvent with different polarity. So we use the non-polar first to elute the non-polar component, and then we gradually increase the polarity of solvent to elute the more polar component. So the concept stationary phase is polar, so it means more polar component will interact with the polar stationary phase. So therefore, polar stationary phase will move slowly compared to the non-polar. So if we use polar mobile phase, which is having more interaction with the polar component, then it will move faster with the mobile phase. Okay. Now, what does it mean by reverse phase? Reverse phase means it's the opposite. Initially, the stationary phase is polar. In the reverse phase, the stationary phase is now non-polar. So therefore, if the stationary is non-polar, it will retain the non-polar component. So the polar component will move faster. Okay, so polar solvents such as water and methanol will be used instead for reverse phase chromatography. Okay. These are used mainly in column. Okay. For example, high performance liquid chromatography (HPLC). Okay, for reverse phase chromatography. So that's the end of learning unit 6. So we have finished all of our learning units in this course. So I wish you all the best for your final exam. Okay, make sure you submit all your assignments, do the quiz, okay, for your carry marks. Okay, so your final will only be is only 40% of your total percentage of this course. So submit all your assignments as well as do the quiz through ELIP to get that carry marks of 60%. Okay, of course it include the midterm as well. Okay, good luck and all the best. Thank you.